Okay, moving right along, we're going to go into the second half of the fluid lubricant fundamentals segment on here. Just a couple of things to keep in mind. You know, we talked about the differences in base fluids between mineral and synthetic and the advantages of synthetics and why there's becoming more and more demand, and that's because of the greater demands that are being placed on lubricants in general nowadays on here. We did, however, talk mostly about just the base fluid itself. And unfortunately, there can be situations in which things exist that can't be addressed by the base fluid. And in those types of situations, we may look towards the use of some type of chemistry to be placed in the base to further address issues or to at least improve other characteristics of the base fluid itself. When we talk about that chemistry, we're basically referring to additives. Virtually all lubricants, fluid lubricants out there are a combination of base fluid, base stock, whatever you want to talk about, and some type of additive chemistry itself. And the reason, again, is because lubricants have to be multifunctional. Certainly wear is an issue. It's a major concern. But there's a lot of other things that are at concern level also in there. Let's kind of take a look at some of the other functions that lubricants are required to perform, and we can see if there's something that perhaps from the world of chemistry that can help us out in those areas. We talked certainly about minimizing friction in wear, and the non-compressibility of the fluid does certainly help us in that situation. Whoops, I'm going to move back one here, sorry about that. It does help us in that situation. There can, however, be situations when we talked about the different lubrication regimes in which contact is still occurring, even though there is an oil film on there. So that could be an issue or a spot that additive chemistry may come and be a value of it. By reducing friction, we are going to reduce the generation of heat. So keeping a piece of equipment cool is going to be beneficial. But heat is going to be generated, and the ability to transfer that heat to an area where it can be safely handled or dispersed is important as well. Seal and prevent contamination. That's kind of a twofold issue in there. First of all, we know that within that engine, there's going to be a lot of dynamic situations in which sealing is important between the cylinder liners and pistons and rings and that type of thing. Oils have to be of the proper viscosity to minimize transfer in those areas. But there's a lot of gaskets and O-rings and seals and this type of thing that are going to be exposed to the lubricant, and there has to be good compatibility there. So when we talk about this particular situation, we're talking about two different elements which concerns can arise. Maintain internal cleanliness. This could be from byproducts of combustion, could be external degrees, could be breakdown of the base material, all forming sludges and varnishes and lacquers, minimizing the cleanliness. That's another issue that has to be addressed, and we're going to try to do that through the lubricant and lubricant chemistry itself. When we talked about fatigue being a wear mechanism on it, again, we talked about its ability of a fluid to dampen shock. And in turn, we're certainly going to reduce the stress on the component, but we're also going to reduce noise within the system itself. So that's something that we're going to want to take a look at too. Prevent rust and corrosion. We said corrosion was an issue. Rust is actually a bigger issue. And to be honest with you, most lubricants, whether they be mineral oil or synthetic, do a very poor job in this respect. You know, everybody thinks, well, you know, you want to keep something from rusting, put some oil on it. At that particular time, usually the oil is only there as a physical barrier, and is only allowing for short-term protection. If we want long-term protection, because that oil film is eventually going to wear off or run off on there, some other type of additive chemistry may be required on there. Energy transfer. Energy transfer, what? Lubricant transferring energy? What are you talking about there? Perfect example is a hydraulic system. Energy is generated at a pump with a motor, transferred to a fluid, then the fluid then transfers that energy to some type of working device. It could be a motor, it could be some kind of actuator, you know, a hydraulic cylinder, could be a number of different things. So that's an issue that we may want to take a look at, and certainly something that is a common requirement of a lubricant. You say, well, in a car, I don't see that. They don't have any hydraulic systems in there. Well, certainly they do. Your hydraulic lifters in the cam area, they're expanded because of hydraulic pressure that's generated by the pump. So there is energy transfer that has to be accommodated through them on there. So really, again, we need the two types of components in there. Some base material, good base material, and generally some type of additive chemistry. Because what this additive chemistry is going to do is either improve characteristics of that base material or impart new properties, new characteristics to it, brand new ones that it didn't have. How much is used? Well, it really depends on the product itself. If we take the first product, which is an extreme pressure gear lubricant on the far left there, additive chemistry is going to make up about anywhere to 5 to 15%, depending on the application, the type of product. 5 to 15% is going to be this additive chemistry in there. If we take a look at the center one there, passenger car motor oil, a lot more things to contend with there. Gear lubricants, we don't have byproducts combustion to deal with. Automotive engine oils, yes we do. It's going to take different or additional additive chemistry. So one would expect to see more in there. Yeah, 25 to 30%. We can see some other more application-specific oils. This happens to be an oil, the oil on the far right, an oil that is directed towards a two-cycle engine. And in this particular case, it's actually toward, let's say, like marine outboards, so on, and that type of situation. 60 to 70% additive. Over half is additive on it. The rest is almost just carrier. It does some other things too. But depending on the application is going to depend how much of these chemistries we have to put in the product itself. Or in some cases we don't have to put in, depending on the base material that we use. Okay, get back to the wear situation. Again, that oil film that the base stock is going to provide may not be adequate. There may be some contact. Again, like in a mixed film type lubrication regime on there. We can add chemistry that can do a number of things. One, it can bond to the metal surfaces and set up an artificial wear surface. So if contact occurs, it's not metal to metal. It's additive to additive. And it'll be worn away, but new will be plated off on it. So that type of chemistry on it. We can have what they call extreme pressure additives. They function somewhat like what anti-wear additives do. However, pressures generally have to be more extreme for these types of additives to function. These additives are strong. They will bond to the contact surfaces on the component itself. And in many cases, they'll actually change the surface metallurgy, harden it up, this type of thing. So it can be a combination of type thing, either a sacrificial wear surface or change the metallurgy of the wear surface so it doesn't wear as rapidly. Again, another chemistry that can be used. Antioxidants. Okay, we talked about the oils breaking down when subjected to heat. There are antioxidant chemistries that can be added that will reduce that. Keep the oil in a suitable condition for longer periods of time under higher operating temperatures. Again, if you have a very, very thermally stable base material, like you'll find with synthetics, the need for this type of additive is minimized. And one of the things, we're going to go through a lot of different additives in here, but the general rule of thumb is don't use an additive unless you have to. So you want to use base materials that have a higher level or provide a higher level of performance over a broader number of issues so you can minimize how much additive is put in there. The reason for that, these oils will only hold so much additive. And if you have to put 20 different additives in there, you're not going to be able to put a lot of all of them in there. But if there are some that you don't need, like antioxidants, if you're using a base material, all of a sudden, now you have room for more of something else. So these additives will take care of a lot of the needs, but really, if you don't need them, you don't want them in there. Okay. Antioxidants, not only will it cause the oil to break down and thicken on there, but it'll cause for the generation of things like sludges or minimize the formation of sludges and varnishes, lacquers, this type of thing. Synthetics are so much better on that. Pour point depressants. When we talked about mineral oils, they tend to contain paraffins. These paraffins are wax molecules, and under normal circumstances, there's no issue with them. Matter of fact, there's actually a bit of a benefit with them. As the temperature of the oil decreases, however, this wax will crystallize and start to agglomerate. And as it agglomerates, forms bigger and bigger structures to the point where it actually causes the oil to solidify. If it solidifies, you can't pump it, so it's no good. So to keep that from happening or reduce its effect, they'll put pour point depressants in oils that have high paraffinic content. This doesn't stop wax crystals from forming, but it inhibits them from agglomerating and forming these large structures. So it allows the oils to be used at significantly lower temperatures. Now, when you look at synthetics don't have paraffins in it. So wax crystallization isn't an issue. So we have good low temperature, or I shouldn't say we, synthetics have good, better low temperature usability, yet they don't need pour point depressants. Again, something else you don't have to put in there, you got room for other stuff. Viscosity index improvers, we talked a bit about that too. These viscosity index that indicates the temperature range that the oil will function in. Viscosity or VI improvers allow you to extend that range depending on how it is. Like I said, to keep the oil from thinning out too much as the temperature increases, VI improvers expand, creating more internal resistance, but they shrink down so they don't really thicken up the oil as much at low temperatures, and they work out quite well. Couple of issues with them though. These VI improvers are very long chain molecules and can be mechanically sheared. They can be mechanically chopped up. And once they're chopped up, they lose their ability to expand and increase internal resistance as the temperature increases. So they lose their effectiveness over time. So really you want to start off with a base material that naturally has a broader viscosity index to begin with. If that's the case, you put less of this in there, or can put less of this VI improvers in there, or maybe none at all. And then if you have none at all, then you're not going to have any shear back, and the oil's not going to thin out on use. Another thing is too, this VI improvers, as well as most all the other additives, are available in different quality grades. There are VI improvers out there that are very, very shear stable. You can't chop those things up if your life depended on it, okay? They will last, you can put them through gears, do anything you want, and they'll just stay and function just like they did when they brand new. They're very expensive though, okay? If you have a cheap base stock and have to put a whole bunch of VI improvers in there, it's going to cost you money. It's going to cost you a lot more if you put the highest quality ones in there. So you're better off to use something with a naturally higher viscosity index to it base stock, and if you have to put some in, some VI improvers, you can put the higher quality ones in there. It costs more, but it's just a little bit more. And you're winding up with a better product. So, there's also what they call temporary shear there. Basically in these VI improvers, as when they run in one direction for a period of time, they tend to align themselves with the direction of flow. And this can cause the viscosity to drop down a bit because there's less resistance. But once the oil gets into a pan, it can sit and soak there for a short period of time, the VI improvers will go back into a random arrangement, and your viscosity goes back up again. On there. Corrosion inhibitors, and I got two parts in here. All right. First of all, you want inhibitors in there that will set up a barrier to keep things like acids, if we're talking about rust corrosion, to keep moisture and oxygen away from the component itself. And they're just additives that have affinity to surface. They go in there and they kind of cover everything. The other type of corrosion is basically when we're dealing with acid neutralization. You'll want something alkaline in that oil to neutralize acids in there. Detergents and detergents from a cleanliness situation, you want chemistry in there that is going to minimize the agglomeration of contaminants, byproducts of combustion, sludge material, this type of thing. Keep it from adhering to components. And that's basically where our detergent packages come in. Detergents also is our major source of alkaline material for acid neutralization. So oils that have high level of detergents in there are likely to do better cleaning. They're likely to have a greater ability to neutralize acids. Dispersants, basically what we're looking at is additives that keep the agglomeration of contaminants from occurring, especially soot. Very, very, or quite an issue when it comes to diesel application. We don't want these contaminants to agglomerate and again form these larger structures. They'll eventually get so big they can no longer be held in suspension in the oil, and they'll fall out as a sludge, a deposit forming type product. These are going to be added on there. There can be other items. Let's say we want to try to get better fuel economy or try to improve the lubricity or slipperiness of of an oil. We can put what they refer to as friction modifiers. Friction modifiers tend to provide additional fuel economy. We see them used quite frequently in automotive engine oils. Before it was always gasoline engine oils, but now we see their use in some diesel application as well. This can be a real benefit as far as picking up additional fuel economy, but it can have some negative effects too. If we look at certain applications, motorcycles come to mind. Those that have a common sump with the engine and the clutch itself, these friction modifiers can reduce the friction within a wet clutch application and cause slipping, which can cause performance problems and longevity issues. So depending on the issue or the application, friction modifiers may be included or may be best to stay away from them. That's one of the reasons why you see differences in oil. You see one company market an oil for cars and trucks and another one specifically for motorcycles. Well, you say, well, they're both internal combustion engines. Why do I need two different ones? Are they really different? If the formulators did their due diligence, you bet they're different. And this may be one of the differences right there. There can be solid lubricants added to the oil to minimize wear, increase protection when we're talking about extreme pressure type situations. Probably one of the ones that are more common, at least to the average consumer, is some form of molybdenum disulfide. We see that as an anti-wear additive in certain engine oils. We see it in greases. We see it used in many other applications. But there can be other ones. Graphite, PTFE, that's Teflon. It has to be a real specialty application to see that one. But they tend to bond to surfaces, or they can reduce the roughness. They can act as EP additives as well. Anti-foam additives. Foam. What are we talking about? A chocolate shake here or what? No. Anytime you start agitating a fluid, you run into the possibility of getting air trapped within that that fluid itself. We see this in engine oils where they're being splashed around and this type of thing. We see it all the time in any lubricant that's lubricating a gearbox, in the gears themselves. All that churning, all that action gets a lot of air entrapped in there. And it's not good for a couple of reasons, and I think I've got them listed in here. The first one, we use an oil or we use a fluid because of its non-compressibility characteristic, right? You put the oil film between two components, it's non-compressible. Theoretically, those two components should never touch. Now suspend air within that oil film. Air is compressible. Now that oil film collapses, and the likelihood of metal-to-metal contact now exists. So you don't want air in there for that reason. Also, too, that air contains oxygen. These air bubbles are now exposing a greater surface area of the oil to oxygen and increasing the risk of oxidation and hence deterioration. You don't want that to happen. There's really nothing we can do to keep that air from suspending in the fluid. It happens, and it's going to happen. We can't stop it from happening. But we can use what they refer to as anti-foam additives. What they do is they reduce the surface tension on the surface of that air bubble and cause it to collapse sooner. So air may be entrapped in there, but these anti-foam additives will cause it to dissipate much more rapidly. What we don't want to do is open up a gearbox, open up a transmission, open up an engine, and see 3 inches of foam in there. That's the sign of a real problem. And maybe it's because the oil doesn't have any anti-foam additive in there. Or maybe it's the sign of the wrong oil being used. Or maybe it's a sign of contamination from another source. That's why those are there. Emulsibility and demulsibility, that's basically, depending on the application, we're going to want that oil to react to water in a certain way. When it comes to engine oils, we want the water to stay in the oil. Stay in the oil? Why would you want it to stay in the oil? Well, we want it to stay in the oil so then the oil can bring it to hotter temperatures where it can be evaporated away. What we don't want that happen is we don't want the oil to cause the water to separate. Because then, let's say like in the oil sump, that water is going to separate from the oil in the sump itself. And where's the oil going to go? Going to go to the top of the sump. The water is going to be on the bottom. Where's the pickup for the oil pump in an automotive engine? It's at the bottom of the oil sump. You get enough water in there and the oil will not hold on to that water. It will separate. You let it sit for a while, you go to start that engine and it's pulling straight water, pumping it up to the rest of the engine components. In a hydraulic system or in a gearbox, we're going to deal with it differently. We want it to separate. So through the use of additives, we can determine how it's going to handle the water itself. And here's an example here. Okay, here's a good, the oil's been, or the water's been emulsified. It's good mixture on here. Here, it separates quite rapidly. You can see the two. And obviously, if the oil pump was down in that lower section, the one on the right there, that could be an issue. Could be an issue. Compressors. We want the water to separate very rapidly, so it's going to demulsify quite quickly. Another thing that we may put in the oil, dyes. Why do we put dyes in there? Dyes don't perform any type of or provide any type of performance improvements or benefits. They're there for identification only. Automatic transmission fluids for cars tend to use all the red dye, where the engine oils will tend to use usually an amber dye, amber color dye. Reason for it? Quick identification. You look under your car, there's a pool of oil there. You can immediately tell if it's coming from the engine or coming from the transmission. Also, too, it can be an indicator that some type of different fluid is in there. Here again, if it's red, well, you certainly know it's not engine oil. You know it's not a gear lubricant. What kind of fluid is? And it may stop you from installing the wrong fluid in it. So, but that's pretty much all they do in there. Seal conditioners. Base materials react with the materials used in the production of seals differently. Some cause this material or these materials to swell, which is great, because what happens as the seal wears, its dimension is reduced. If the oil causes it to swell, that could make up for that loss in material. So maybe a little swelling's good. But how about if it balloons it up and makes it real soft? So now it wears at a higher rate. That would not be any good at all. Or what happens if it negatively reacts with the seal and causes it to become brittle? Now it could crack or wear at a higher rate. You want to make sure that whatever oil is being formulated, that the chemistry and the base materials are such that they have perfect compatibility with the type of elastomers, the seals, the O-rings, that type of thing that are in the application. And that may be another reason why an oil is labeled as application specific. Now, many base materials, some base materials tend to be more compatible with these materials than others. But that doesn't mean they can't be used or shouldn't be used. There are additives, or there are the other material that can be added to the oil to change the way it reacts with these materials. One of the things that many people do is synthetics. There are certain synthetics, PAOs for example, which tend to be very neutral when it comes to these type materials. They don't cause them to swell, they don't cause them to harden, they don't do anything. But like we said, maybe a little swelling is a good thing. There are other synthetics, esters for example, that like to cause them to swell. Unfortunately, if not done properly, esters can cause too much swelling. So maybe a good combination is maybe most of it's PAO, but maybe throw a little ester in there. Take care of the swell situation. You get the best of both worlds. That's why I say a lot of this combination of base materials happens. And it's better to do it that way than add some other type of chemistry in there as an additive. Because here again, base material can only hold so much additive in it. Okay, on this, I'm not going to go over this in real detail. What I want you to get from that, or from this, is base materials have certain traits. We all know the basic functions that oil has to provide. This kind of goes over what traits the base material has to address that function, and what may be addressed using supporting additive chemistry. And a lot of these things duplicate the friction and wear. Well, obviously the base oil viscosity is key. We know that right offhand. Is there any lubricity characteristics? Certain base materials have what they refer to as lubricity characteristics, which tend to make them a little more slippery, a little better lubricants than others. And shear stability. Okay, why do we say shear stability? Well, if the oil loses its viscosity, it's not shear stable, friction and wear is going to be an issue. Maybe not originally, but down the road. But from a supporting standpoint, are any anti-wear or EP additives are going to address friction and wear. VI improvers. Why VI improvers? Because they're going to maintain the viscosity at higher temperatures. Maintaining the viscosity, higher viscosity, better wear, protection, da-da-da. You understand where I'm going on here. Secondary things, pour point depressants. Why would they be associated at all with the function of friction and wear reduction? On it. The big thing there is if the oil gels up on you because of paraffin or wax formations in there, you're not going to pump any oil, it's going to be an issue. So anti-foam, we know that. We get air in there, compressibility, that's an issue. And friction modifiers, again, can help the thing out. Solvency, again, we have a similar type situation there. You can't just look at the base material. You can't just look at the additive chemistry. You want to look at them both. It's a package deal. Okay. Moving parts, again, I'm not going to spend a lot of time on this, but there's relationships between both of them there. Shock dampening, again, that's more viscosity oriented. Wear protection, you see, or excuse me, corrosion protection, that's all additive chemistry really. Couple of things. Never intentionally mix different lubricants because the additive chemistry may be different. Okay, is this going to cause the tires to fall off your car? Is it going to cause you to lose the FM radio reception? You know, no, it's not. But long term, yeah, it can be an issue. It can be an issue. We get into some specialty application, some specialty industrial applications. Mixing two can cause very, very rapid problems and very significant issues. So we don't want you to intentionally mix. Generally speaking, if you're talking about, let's say, like motor oils for cars and trucks, usually compatibility with the competition is something that's always looked during formulation. No credible manufacturer is going to provide you with an oil knowing that there is a real good chance of a serious compatibility issue out in the field. So, additive performance varies. It varies on how much of the additive is in the oil and the quality of the additive itself. Okay? Two things there. And certain additives can present disadvantages. I've got a couple of examples here. One, these were looking at basically one additive type, two different brands. All right? And we're looking at acid control, and we can see the difference between the two different brands or two different styles of the same type of additive. One basically provides protection twice as long as the other. So some of these differences in performance can be huge, but it always comes at a price. If you're looking for lowest quality, or if lowest price is all you're interested in, don't expect to have high treat levels of additives in the oil or the best quality stuff. You will get the absolute minimum. Absolute minimum. You will have no safety margin. You're just going to get the absolute minimum performance. Here's another one too. These are anti-wear and EP additives. A lot of people think, well, if I add these things in, it's going to help me out. It's only going to help you out if you really have an issue. Extreme pressure additives, for example, are generally used in gear lubes. Why are they used in gear lubes? Especially like when we're dealing with hypoid gear setups, the sliding pressures and everything like that are such, they're significantly greater than found in an automotive application, and to combat that, they need a different type of chemistry. That same chemistry isn't compatible in an internal combustion engine. Matter of fact, when you take a look at strong EP additives, for example, and that is the one here on the far right, you can see that, yes, if the loads are sufficient, it can minimize friction. If that degree of load doesn't exist, if it's lighter than that, it actually causes more internal resistance and restriction and friction within the oil. So not only have you wasted money putting something in there that isn't providing additional benefit, it's actually presenting a negative. It's causing more friction than if you didn't have it in there. That's why I say, if it doesn't need it, don't put it in. Types of additive or where additives are used. Here's kind of a general overview. List different products on the left-hand side and the different types of additives that are likely to be found in there. It's going to vary depending on the application, how that product was directed to, so on and so forth. But it can be a wider range. In some, it can be very, very few additives. Iron oils, for example. They have rust and oxidation inhibitors. That's all that's in there. They're probably one of the purest products that are out there. When we take a look at some of the other ones, what's a good, engine oils are good. ATF fluids tend to be a lot of additives in them. But it's just to give you somewhat of an understanding. And it depends a lot on the application. So, a couple of final thoughts on it. We talked about performance is going to vary depending on the application for which the product was actually directed and formulated for. And also, performance is going to vary depending on the base stock and the additive package. Not only type of additive, but quantity of additive. One trick pony, okay? Alrighty. Basically what I'm talking about here is the people that are out selling the miracle oil additive. You know, one additive that is going to eliminate all your wear, one additive that is going to allow your oil to last forever. This stuff doesn't exist. And if it does, let's say minimize wear, it's only going to address one issue. And how well it actually addresses that issue can be very debatable. For example, a lot of anti-wear additives have an affinity to surface. All right? You get a lot of surface in the engine and it just goes in and plates out on it. Well, you got a slug of it in the oil that you formulated. Now somebody comes in and puts 3 or 4 times as much in there. Detergents have an affinity to surface. Okay? You have so much anti-wear additive in there, and it's basically soaking up all the surface. The other additives can't function. It's a very, very sophisticated, and it can be easily altered by adding large amounts of other chemistry to it. So don't go for, if you think that your oil has a deficiency to it, my advice has always been, take the money that you would spend on one of these aftermarket additives, take that and add that to the normal amount of money you'd spend for an oil change, and that higher amount now, go out and buy a higher quality oil. Don't try to mess around with the chemistry on it. Really, only when an oil, the base stock, and the additive package is formulated to address all of the issues, all of the concerns relating to any given application, will you receive the maximum level of protection, performance, and economics. And that's it. Thank you much.